Hello and welcome back to Lesson 1. Before we start to dive into some of the theory that you'll need to learn or revise for this course, let's put everything into some context. What I'd like to do in this part of Lesson 1 is to make sure that you're familiar with one of the most important polymer processing machines, the extruder. Whilst it's recognised that not all polymer processing operations involve extrusion at some point, a lot of them do. So let's start by taking a look at extruders and by seeing how they work. So there are two basic types of extruder, a single screw extruder and a twin screw extruder. We're going to start by talking about the single screw extruder because it's by far the most simplest machine that you can find. So if we look at the anatomy of a single screw extruder, you start with something to drive the machinery. So you've got a motor and typically a gearbox, which may be either single-phase electrical supply or usually three-phase electrical supply for most machines of an industrial scale. And then what you have is a barrel, a heated barrel, that effectively defines the flow path through which the molten material is going to be flowed. Now, the heating is provided typically by band heaters or cartridge heaters, and on most extrusion lines you can usually see these clamped around the outside of the barrel. Very, very obvious where they are. The next component we have is the meat of the machinery. We've got the extrusion screw. This is driven by the motor and the gearbox, and it's responsible for conveying the materials from the material feed, which is typically in some kind of hopper. And from that material feed, the material is then transported, if you like, by an Archimedean screw, to a different part of the screw, which is a little bit different in diameter. And then typically what you have is the ability of the machine to compact the material, pressurize it a bit, and then to pump it. So the extrusion screw, which we'll talk about more in a minute, actually does a lot. In terms of the basic material that's fed into these machines, it tends to be a pelletized polymer feed, a little bit like that I've shown in the picture there. Single screw extruders typically aren't that great with things like powder feeds, for example. So we've got our drive, we've got our material supply bin, our hopper, we've got our barrel through which the extrusion screw pushes the material and the material melts under the action of the heat supply from the heaters. What we then have is the shape-forming device at the end of the extruder, the extrusion die. And so typically the extrusion die requires quite a lot of very careful design in order to get the final shape and form of the product that you want. And in lessons that follow, we'll be exploring why such careful design is required. But I'll give you a bit of a teaser. It's all down to the nature of the materials that are processed. Some materials are very easy to process and retain their shape. Some materials are very tricky to process and they don't retain their shape because of retained stress within the material as it's processed. So let's look at the extrusion screw in a little more detail because it's a very important piece of machinery within the extruder as it provides the conveyance, the compacting, the pressurization and the pumping of the molten material. There on the whiteboard I've shown a very basic diagram of the simplest type of extrusion screw that you're going to find in a single screw extruder. There are far more complex designs than this, but let's start at the beginning. You can divide an extrusion screw of this nature into basically three zones. The first bit, the feed zone, sits beneath the hopper, and its function is purely conveyance. So it's a little bit like an Archimedes screw, just conveying the polymer pellets from where the hopper enters the barrel to the next point on the screw. As the material is conveyed, it's also compacted somewhat. The next zone of the screw is what's termed the compression zone. This is where a lot of the melting of the material happens, and also where a lot of the pressure in the machine is generated. Now, as we'll see in a minute, extruders can generate very large pressures, hundreds of bar if needs be, and this is the part of the screw where that pressurization actually happens. The final part of the screw, and you'll note that the final part of the screw has a far larger diameter internal shank, so the depth between the largest diameter part of the screw, the outer part of the flights, and the smallest diameter part of the screw, the outer part of the core of the screw if you want, is the metering zone. And this really is where the material is pumped at a given volumetric flow rate. So there you have it, 3 zones on a single screw extruder screw. You've got your feed zone, which has deep flights. You've got your compression zone, where the internal diameter of the screw goes from small to large and where compression happens. And then you've got the metering section of the screw, which is where you've got a fairly large internal diameter and fairly shallow flights. So let's talk about when and when not you might use a single screw extruder. As I mentioned before, if you need to pressurize materials for shape forming to a very high pressure, then these are very, very good machines to use, because don't forget, molten polymers tend to be very, very viscous, as well as being quite elastic. But if you look at the zero shear rate viscosity of, say, a molten polyethylene at, say, 150 degrees Celsius, then you're looking order of magnitude, very roughly, about 10,000 Pascal seconds. Compare that to water at 1 millipascal second, and you'll see why it's very easy to generate very high pressures, and why it's necessary to generate very high pressures to actually move these materials through their flow path. So extrusion devices tend to be high pressure, and single screw extruders can attain throughputs of the order of tons per hour of finished product. So they're very large throughput, which is very, very handy. So the strengths of a single screw extruder is that they're cheap. They're pretty simple machines. Mechanically, there's not a great deal to go wrong. And they're also rather easy to maintain. Everything's modular. You can take the barrel off, you can take the screw out, you can take the heaters off, you can take the hopper off, you can take the die off. You can either clean them physically or clean them thermally. You can roast off polymer that you don't want there anymore, or you can chemically treat them. So it's very easy to take to pieces, very easy to maintain, very easy to put back together, which is a big benefit. Where single screw extruders aren't so strong is when you're dealing with complex materials. So for example, if you've got a multiple feed material where you might start with a base polymer and then a little while later add something else to it, it's not that great for that, because single screw extruders typically aren't that great at mixing. There are things you can do with single screw extruders to assist mixing. There's static mixers. To a point, you can redesign your screw to include mixing zones, but they're never going to be as efficient at mixing as, say, a twin screw extruder. If you're looking to maximize energy efficiency, single screw extruders aren't the most energy efficient typically. A twin screw device will probably be better. Also, if you're doing something experimentally or in an R&D context and you want to change the machine configuration a lot, maybe add different amounts of mixing or conveying or kneading, a single screw extruder isn't going to perform very well in that context either. But they are an absolute workhorse of the polymer processing industry, where you've got relatively straightforward materials, pelletized polymer, that you need to mass produce at high throughput. And so they're great for processing thermoplastics, but they're not so great for, say, compounding or dealing with multi-component systems. So let's have a look at what one of these machines actually looks like. I've shown you this diagram before on the whiteboard, which is rather crude in terms of its nature, but we can relate the components that I've put on that diagram to what you see on a machine in real life. So there's a picture of a small to medium-sized extrusion line. If somebody was standing next to it, the top of the hopper, which is on the left-hand side, the highest part of the machine, that sort of blue trapezoid, would reach, say, to somebody's chest, something along those lines. So that gives you an idea of scale. You can see the heated barrel very, very clearly. The silver devices there, you can see down the line, are where the heaters are. Right at the far end of the machine, you've got that great clamp and that great big grey bit, and that is where the extrusion die is clamped onto the barrel. And then you can see to the right-hand side of that, there's a little bit more downstream processing, takeoffs and all the rest of it. On the far left of the machine, you can see that's where you have your motor drive and your gearbox, the big blue bits of machinery. So it's all very visceral. You can look at one of these machines and you can see exactly the bits and pieces that relate to this diagram. The one thing, of course, that's occluded is the screw, because that's sitting inside the barrel. But if one was to look down through an empty hopper, you would see the conveying zone of the extrusion screw. So I've mentioned in passing that there is another configuration of extruder, the twin screw extruder. So let's spend a little bit of time now looking at one of those. I'm going to show you a diagram in top view, because if we looked at a twin screw extruder in side view, we wouldn't see that much difference to a single screw extruder. But if we look in top view, we can start to see some similarities and we can start to see some differences. So life starts with whatever energy source drives the screws, in this case again a motor and a gearbox. Then again we have a barrel which defines the flow path through which the molten material is going to flow. And around that barrel again are band heaters, or inserted within the barrel are cartridge heaters, a means of giving heat input to the system. Because if you're dealing with a thermoplastic, say, you need to be able to melt the solid to start with. So that's very, very similar to your single screw extruder. Now let's look at where things change. As the name suggests, you actually have two extrusion screws side by side. And once you've got two extrusion screws side by side, you can start to do all sorts of different things, because you can design these screws in a modular fashion, and you can include means of course, conveying, because we need to move material, but also mixing and additional pumping and kneading components as well. And we'll look at this in a little bit more detail in a second. So you've got two screws, and then at the end of these screws, one has one extrusion die, which is again the shape forming element, and again the same things apply here in terms of die design as it does to single screw extruders. It can be quite tricky and it can be very material dependent. So the final thing that we need to add to this line is a means of getting material in. Now, I've included on the diagram a single hopper. It's the simplest configuration, but please do bear in mind that with a twin screw machine it's perfectly possible and sometimes usual to design in multiple feed points for different materials you may want to mix together during the extrusion process. So even though I've illustrated a single hopper, that is not an exhaustive example. So I've mentioned that you can do a lot more with a twin screw extruder than you can with a single screw extruder. Let's look why. And it all comes down to the screws, the screw configuration, and the screw design. So screws can either counter-rotate, rotate in opposite senses, or they can co-rotate, rotate in the same sense. They can be, as the diagram I showed suggested, be parallel. Or there are other designs where your screws actually converge together and give more pressure to the material as it translates down the barrel. The screws can also be designed to intermesh, as in the flights overlap, or not intermesh, as in the flights don't overlap. And so there's a lot of variety that one can see in the way that you can design twin screw systems, hence you can customize them for very, very specific applications. So let's have a look at some pictures of some twin screws. There on the whiteboard is a typical twin screw, and you can see immediately that there's different elements along the length of it. Let's have a look at some of these elements. You might, for example, include geary type things, and you can see at the far end with the purple arrow there. Now these are typically mixing elements, and it's when these two geary things intermesh, screw to screw rather than screw to barrel, that you get that mixing happening. You can do other things as well. For example, those lobe-shaped elements are actually kneading elements. Twin screw extruders have great application, for example, in the food industry, and you may there be mixing together all sorts of different types of material and performing, say, extrusion cooking. And so good homogeneous mixing becomes very important at that stage, and those are some of the elements that one might choose to do that. Also, we can see in common with the single screw, you've got conveying elements, because you have to move material from one zone of the screw to the next zone of the screw, and you also have to be able to pressurize material and pump material. And so conveying elements become important for both of those duties. Again, it's good to see what these machines look like. It's a big blue machine with a big grey barrel. It looks a little bit different configurationally from the single screw extruder, because the barrel is now typically sort of rectangular in section. Typically they're clamshell devices that can open up to expose both of the screws. And so you've got typically cartridge heaters inserted in a rectangular block rather than band heaters clamped around the outside of a cylindrical barrel. But all the elements that we see within the single screw are there in the twin screw. You've got your motor drive at the far end. The motor's a big silver thing, connected to a big yellow gearbox. And then you've got your twin screws and the barrel in which those screws sit, and that's the big long grey thing. And at the far end, a slightly buff or beige coloured element is the extrusion die. So Twin screw extruders are great for complex materials and processing complex materials. I've mentioned extrusion cooking in the food industry. That's one thing you can do. You can also, for example, mix colours within these machines. And what I mean by that is, say, for example, you're producing a shower rail of a prismatic cross-section, maybe a cylindrical cross-section or a splined cross-section, and the market wants them to be pink. So you'd put in maybe polypropylene as your base polymer and maybe 2% of colouring agent. But you want that colour very well mixed within the base polymer, and so you could design an extrusion screw within a twin screw device to do that mixing for you. And we call that addition of colour a master batch, because you've got a small amount of colour in a large amount of material. You also can process filled materials, for example glass fibre reinforced materials in these machines as well. They're also very good for powder feeds as well, and sometimes one wishes to mix powder feeds or sometimes even liquid feeds into a extrusion line as you process the material. And again, coming back to the food industry, these additional liquid feeds might be flavours, or they might be sweeteners, or something of that nature. So twin screw machines can be designed to handle complex feeds for complex materials. Twin screw machines are less sympathetic on the triple bottom line. They're expensive machines. The rule of thumb I always used to work to is twin screw machines are roughly an order of magnitude more expensive than single screw machines, although naturally prices change over time and relative price also changes over time. So let's summarise a few key points. Extruders are really important. They are typically the workhorse of the polymer processing and sometimes the food processing industry, so we need to know a bit about them. And later on in this course, you're going to learn a lot more about them. But between now and then, we're going to be mentioning extrusion quite a lot in passing, and so right up front, I want you to know what it's all about. Typically, you've got two machines. You've got single screw extruders, less expensive, well suited for melt processing of pelletized single component resins. They're also a little bit poor for mixing, and they're not so strong with processing multi-material products where you need to add many materials into the same extrusion line. Twin screw extruders are more expensive, but they're very, very customizable and very, very adaptable, and they tend to excel at duties where you've got multiple feeds, non-pelletized materials, and those systems that need a lot of mixing.